So today we're going to look at problem 1.2, which says the heat flux that is applied to the left face of a plane wall is Q double prime equals 20 watts per meter squared. The wall is of thickness L equals 10 millimeters and of thermal conductivity K equals 12 watts per meter K. If the surface temperatures of the wall are measured to be 50 degrees Celsius on the left side and 30 degrees Celsius on the right side, do steady state conditions exist? So we're going to start with our usual format, and that is by writing down what are the knowns. So first off, we know that Q double prime, or the heat flux, is equal to 20 watts per square meter. We know the wall has thickness L equals 10 millimeters. We know thermal conductivity is K equals 12 watts per meter Kelvin. And finally, we know that T left, the temperature on the left side, is 50 degrees Celsius, and T right on the right side is 30 degrees Celsius. Okay, and next, what do we need to find? And the problem just asks us, do steady state conditions exist? So we just need to find, do steady state conditions exist? Okay, next we're going to draw our schematic of the situation. So first I'm just going to draw a little plane wall, which I'll draw these squiggly lines to indicate that it goes, it's broken in that direction. So this is extending into space. And I'm going to mark a couple things. So first we have T left on the left over here and T right on the right. We know that this thickness here is L, which was 10 millimeters. We know that we have thermal conductivity K applied to this. And the last thing I'm going to add is that we know the heat flux. So I'll draw a little squiggly arrow here, and we know the heat flux Q double prime. I'm just going to move that schematic up a tiny bit. Great. Now that we've drawn our schematic, we can move on to our assumptions. So in this problem, well, we can't exactly assume steady state because that would defeat the purpose of the problem. So first we're going to start by assuming 1D heat transfer, or in this case, conduction. So just in one direction. We're going to assume constant properties, although you could argue that there's no reason to think the properties would change. And similarly, no internal energy generation. Okay, now we can move on to our analysis. So how do we tackle this problem? We are trying to find whether the conditions for steady state exist. So what does that mean? If we have steady state in a system, that means the things that are going into the system are the same as the things that are going out of the system, which in this case means we're trying to figure out if the heat going into the system is equal to the heat going out of the system. And in order to figure that out, I'm going to go back to our schematic and draw a control volume around it, which, if you're not familiar, is basically just an imaginary box. And we're going to look at the heat transfer relative to this box. Okay? So we're going to figure out if the Q going into this box is the same as the Q flowing through this box is the same as the Q flowing out of this box. And these should all be double primes. So we need Q in to equal Q, we can call this Q conduction, to equal Q out. And if those three things are equal, then we know we will have steady state. So first off, we are given Q in, right? We are given that the heat flux applied to that left surface is equal to 20 watts per meter squared. So now, this is Q in. We just need to calculate Q cond, or Q out, and see if it is equal to 20. If it's equal, then we do have steady state. If it's not, we don't. So I'm going to calculate Q of conduction. And if you don't remember the formula off the top of your head, you can just remember the regular formula, which is pretty similar, that Q equals negative K A dt dx, which implies if we divide both sides by A, that Q double prime, the heat flux, equals negative K dt dx. So knowing that, we're going to say Q double prime conduction equals minus K dt dx. And then I'm just going to fill in the variables here. So for K, we were given that K equals 12 watts per meter Kelvin. We know that dt is going to be T left minus T right. And I'm just going to skip a step here and fill in that that was 50 degrees Celsius minus 30 degrees Celsius. You could skip a step and just write 20 here if you do that in your head. And the dx, or the thickness that the heat has to transfer through, is the same as the thickness L in our schematic. And that was equal to 10 millimeters, which I am going to simplify to 10 times 10 to the minus 3 meters to keep everything in SI units. And then just to check, I'm going to see if my units check out. This Kelvin can cancel with the Celsius, since Kelvin is just Celsius with a value added. And then we're going to be left with watts per meter times meter, so watts per meter squared, which is exactly what we want. And if we do this calculation, we see that we get 24,000 watts per meter squared. And you might notice that 24,000 is not equal to 20, which is crazy. So we can say that we do not have steady state in this problem because the heat flux going into the system is not equal to the heat flowing through the system. Q in is not equal to Q cond, or Q conduction. And that's our answer. And just to finish up, we will put our comments section. One thing that's kind of interesting is we can calculate what the temperature difference would be if we eventually just let this system run for several minutes, maybe several hours, and let it get to steady state. Meaning that the system is just stable. The amount of heat going in is the same as the amount of heat going out, so the temperatures are not going to change. So we can start by using our trusty equation, we'll say Q double prime equals minus K dt dx, and then we want to find dt. So we're going to say that that equation implies that dt is equal to Q double prime dx over K. And all I did there was rearrange, so I divided both sides of this equation. We divided by K, and then we multiplied by dx. And if I fill this in, we can see that that would be 20 watts per meter squared times dx, which was L, which was 10 millimeters, or 10 times 10 to the minus 3 meters. And finally, K was 12 watts per meter Kelvin. And that gives us 0.0167 Kelvin, which is much smaller than the expected temperature difference, of 20 degrees Celsius. And that's the problem.